All right, welcome everybody. Coffee with Caleffi. This is Bob Hot Rod Rohr. We're up in Milwaukee. I got my whole team here. I got my staff and one psychiatrist to help us through this. So I'm going to go through a couple of housekeeping slides, and then we're going to try this new format where we open it up. So thanks everybody for tuning in, and here we go. Today we'll be talking about the topics in number 18, water quality. Now I know we've done water quality a couple times before, but we're getting a lot of questions about this, a lot of concerns, a lot of interest. So we thought we would do this in a format that we can answer your questions instead of, they dribble in weeks by weeks. And I think everybody benefits if we could do it in a format like this where everybody gets the same answer at the same time. So that's going to lead us up to where we're going next. So we're going to talk about the two typical types of closed-loop systems. And by closed-loop, I mean a sealed, pressurized system. Open systems to me would be like a combined domestic water heating system. We just want to focus on the two types of systems that are most common in the hydronic world, the geo world, the solar world, which is water or glycol. So a couple pictures of some jobs that were sent to us recently that show some nice work. There's some of our products used and stuff like that. So that's the systems that we're going to focus on today. All right, so here's poll question number one. In your experience, which has been the most problematic, and we're asking you to choose one, and as you can see, we made this hard. We want to really focus in on what the most common problem is out there, and then we're going to give you a couple seconds here to Woody's going to run this poll to answer this question, and then we'll chat about it. So there's the poll. Thanks, Woody. Right on the ball.
And by the way, on these polls, if there's an answer that doesn't apply, if none of the answers apply to you, better just to skip the poll. We're looking for folks that have some experience on the particular issue. So we think most people will answer, but just in case you feel like you don't have an answer, you don't have to answer.
Yeah, so corrosion, scale formation, sludge debris accumulation, certainly one about antifreeze for you glycoholics out there, and then the maintenance, if you are using the additives, the maintenance of that.
And these are in line with the type of questions I think that come in, Kevin, right on our technical support line. Yeah. People have questions concerning managing corrosion and the maintenance of chemicals and the like. So.
Oh, well, it's all over the board a little bit. We thought there'd be a big standout, but thanks.
Well, this is interesting. So the leading result was scale formation. 30% was the primary issue with fluid quality. We probably would have guessed it would be a high runner from the phone calls that we get and the things that we see from the field. Interesting, Bob, and Jody and Kevin, Mike, Rex, we see sludge and debris accumulation as a big issue, bigger than I think we probably would have expected, right?
And I would say that's in some of the areas where there's a non-barrier tubing that was put in over the years. Again, we don't know who's responding to these, but certainly if it's the western states where a lot of that tubing was put in, that would make sense because that is, when we start plugging up the system. So,
well, managing the fluid quality too, as far as if someone were to define sludge and define debris, they might have different definitions.
Yeah, right.
Sludge could be that soft matter from precipitating out from perhaps maybe chemicals getting added.
Yeah.
People could also address sludge as being that, iron oxide that basically could erode away from the walls of the system and find its way somewhere and accumulate. So obviously, it's both are probably issues. It looks like here. Yeah. And I think surprisingly low was loss of antifreeze property. I think that's being managed pretty well out in the marketplace. But look at maintenance of chemical additives. That's a pretty big one too. So. Yeah. A few surprises there for us.
Okay, well, let's go on to the discussion about that.
So Woody can close the poll and see what people see here. Okay, they're back.
Oh, the poll. What's my other?
Okay. All right.
All right, so let's define good fluid quality. So we want a fluid in there that allows the minimal amount of corrosion, whether it's oxidation, galvanic, where you've got the similar metals in there, iron-consuming bacteria, kind of a rare one out there. It's possible. There's ways to know that when you have it in the system, but it certainly falls under that. Allows a minimum amount of scale formation, like we're talking white lime scale formation. Typically, that's, you see that in domestic water applications too, but possesses minimal amount of loose sediment. You know, we call that sometimes turbidity under a certain micron rating. That's kind of when you hold a glass up and you see a little cloudiness to the water, that's sometimes called turbidity. And then, of course, in glycol systems, that would make sure that the inhibitor package in there is staying up, you know, that it occasionally needs boosted, which we can test with pH meters and different meters. So that's kind of our how we see it. Are we taking questions yet? We want to do another slide there.
No hands up yet. Okay, I think this is how we would define good fluid quality, but you know, there's some conditions in there. I think you said turbidity. I mean, we don't have turbidity in here, but if someone wants to use river water, which we've had questions on, river source water, that might have some silt. Yeah. All right, and otherwise be fine with you know, hardness and total dissolved solids and the like. You know, that might not be so good because that turbidity can either A, be abrasive, or B, end up as sediment somewhere, right? So there's probably a long list of, and there's also different types of corrosion, right? So yeah, we just listed probably two of the most primary, with perhaps the top two, but I think folks on the phone could probably agree that there's a lot of different types of corrosion. So anyway, that's just more commentary on how we define fluid quality. Yeah.
All right, switching on here, corrosion.
So we're going to go through each of these particular definitions of fluid quality one at a time. We'll start with corrosion, we'll get into lime scaling, we'll get into chemicals, we'll get into antifreeze. And, you know, Bob, if we go beyond 60 minutes, we haven't gone too far through this and people are still on, perhaps we extend it. And if this is a really good format for folks to learn from, April is available for us to do like a series 2, if that's what so we'll play that one by ear as we go through the hour.
Yeah, we'll see how many questions and hands go up and where we can go. And at any point now, you can start asking questions too. If the slides that we talked about, if you've got something to add there, a question about that, now's the time.
So we have another poll question that will come up, number 2. Woody's going to throw that in. It's concerning corrosion, okay? And so the poll question is, there it is. In your experience, which corrosion issue has been most problematic? Oxidation corrosion, galvanic corrosion, iron or sulfur bacteria-induced corrosion, or microbial, I guess you could say, erosion corrosion, or I'm not sure. So in your experience, we saw corrosion was a pretty big answer in terms of occurrences of problems out there. Yeah. In your experience, where would you rate these particular types of corrosion in terms of their being most problematic? So let's give 2 more seconds, and then we can close it and post the results. That's interesting as well. Oxidation corrosion, by far the number 1. Galvanic corrosion, I think we all hear about galvanic corrosion. It's number 3. I'm not sure. Isn't surprising, right? Because the effects, what type of corrosion, what's what, is sometimes confusing if you look at the effects. So what was basically corrosion resulting from oxidation corrosion versus a corrosion from pH that is basically very, very low, and that would be called acidic corrosion. So but everyone kind of knows oxidation corrosion, right? So I think as a result, scored high. Yeah. So let's close that. We're going to discuss the corrosion here a little bit, and then we're going to ask questions about corrosion that you might have, if any. So if you want to go on to the next slide after Woody. Okay. So the 2 leading corrosion answers you gave was, as we expected, oxidation corrosion and galvanic corrosion. And here are 2 examples of those particular ones. They're similar. In fact, they're almost identical in terms of how they go about. They're electrochemical in nature. And what happens is that on oxidation corrosion, well, let's go down to galvanic corrosion. You need to have dissimilar metals to have corrosion. And in the case of the T in the bottom, you have a brass or bronze T that has a steel pipe screwed into it. So direct metal on metal contact of dissimilar metals, and combined with water that is conductive, you can see the effects, and that's usually the telltale sign of galvanic corrosion. You see that kind of that oxide, and we've seen that on jobs that we've gone out, that buildup of oxide on the outside as it's corroded. it looks like it's corroded from the outside, but it's definitely corroded on the inside as well. Now on the left-hand side, that's not different metals. That's one metal that got cut in half, and we can see this is oxidation corrosion. Basically, oxygen has created cells in the same metal, dissimilar cells by different concentrations of oxygen located adjacent to one another. And so as a result, we see the effects of oxidation corrosion, even though it's one type of metal. So.
Yeah. And the key to that galvanic corrosion is you've got to have an electrolyte in there. So the fluid is becoming the electrolyte, and the high TDS, which we're going to get to, fluid is what really enhances that corrosion. It's just like the battery. You take the acid out of the battery, you take the electrolyte out, and the cells in the battery, the current goes away. So that one on the bottom, and sometimes that can be confused. It's just a leak pipe where it wasn't tightened properly or sealed properly. But usually when you see the green and you see the barnacles and stuff like that, and if you scrape that, you would see it's actually eating away at the pipe. It's not just a deposit from a drip or a leak on the floor. It's actually starting to, go against the go after those metals in that system there. So
let's run another poll question, and then we'll ask questions concerning the issue of corrosion. So we're going to ask a poll question that is addressing this type of corrosion that you just saw, and that was oxidation corrosion and galvanic corrosion, the two leading corrosions as you guys answered. So the question is going to come up here. It is up there. If you could only control one corrosion factor, which would you choose? Okay. Now we're forcing you to have just one choice here, even though you might otherwise put a couple of choices in there, just to see where people rank the importance of certain water chemistry aspects as it relates to corrosion. So you can add, you say pH, or the concentration of dissolved oxygen, or the value of the total dissolved solids, alkalinity, or contaminants in the water, such as sulfates, nitrates, chlorides. So in your experience, which one would you choose as if you had to control one in order to keep corrosion under control? So let's go ahead and keep that open for another second or two. Okay. All right. So dissolved oxygen is almost 50%. pH is 34%. Total dissolved solids is 10%. Alkalinity very low, and then contaminants is 10%. So I think probably the dissolved oxygen probably doesn't surprise us, the answer. I think everyone understands the role of oxygen in corrosion. Yeah. Just look at your brakes on your car, right? Sometimes your disc breaks and then you see water on your brake set and you haven't used your car in a while, right? They rust up. But pH, a high pH. So let's close this up and let's talk about, pull up this.
Yeah, it takes me to slides or every time I close the poll for some reason. That's all right.
Okay. So this is an interesting graph that explains the role of dissolved oxygen in water and the fluid's conductivity. The two work together, and they interact in terms of their combination effect on whether or not you have a chance for corrosion in your system. So along the bottom axis, you see dissolved oxygen concentration. And this is in parts per meter or parts per million, which is the same as milligrams per liter. And so that's along the x-axis. Along the y-axis, you see total dissolved solids in parts per million. And what this is really saying is that you can control corrosion largely for most metals by either A, limiting the amount of dissolved oxygen in your system, or B, reducing your total dissolved content. Okay? So as an example, if you look along the y-axis to total dissolved content, you see a blue line at 64 parts per million. All right? And then if you look at the curved graph, you can see as it goes off left to right on the far right side, you can see anything, if you have total dissolved solids or non-conductive water, if you say, of 40 parts per million, then it doesn't make any difference how much oxygen you have dissolved in your system because there is no conductivity in the water, very little. And we like to explain corrosion is kind of like, in analogy terms, like your car battery. All right, in order for you to start your car, which is creating work, you have to have A, a strong battery, and B, good battery cables. All right. If you have a weak battery, you can't start your car. If you have battery cables that don't conduct electricity very well, you can't start your car. So the battery is similar to dissolved oxygen. Dissolved oxygen is kind of the catalyst or the potential in your water to create corrosion, and the total dissolved solids, which is a measure of conductivity, is your battery cables. Eliminating one or the other, or preferably minimizing both, will largely protect the system from corrosion, with one exception we'll talk about a little bit later as it relates to pH. The role of pH comes into play in certain metals. As an example, aluminum. One of the primary factors of aluminum corrosion potential is pH levels. And so aluminum is especially sensitive, as all the metals, amongst all the metals in a hydronic system for corrosion, if pH gets out of a range that it feels comfortable in, and each metal has their comfort range. In the case of aluminum, Bob, I think, and Calvin, we've seen mostly 6.5 to 8.5 is kind of that happy range, if you will. If you have a pH, even if you have no dissolved oxygen in your system and your pH rises above 8.5, it will cause the aluminum to begin, the protective layer on the aluminum that's been created, to break down and then start corroding. So aluminum is especially sensitive to pH. Outside of that, pH is more of an indicator that things are okay. We'll get into that in a little bit. As long as they in a range that is happy with metals, and typically that range is about 8 pH. Most metals with a pH of 8, whether it's aluminum or copper or stainless steel or iron, are going to be happy unless something else gets out of hand in the system, such as a lot of oxygen dissolved or conductivity. So I talked way probably too much on that, but I wanted to explain this somewhat complicated factor of corrosion.
How's everybody doing out there? Is there questions or comments, or if we're going too fast, or need something that explain that? I mean, now, let us know. Talk to us a little bit, and we don't want to go through something too fast.
A good question just came in, and I don't know if he has a mic, but he said, how can you measure dissolved solids? Dissolved oxygen. And it's a good question, because typically measuring dissolved oxygen is going to require some pretty heady instrumentation, right? However, the ability to measure total dissolved solids is pretty easy, because it's proportional to the conductivity in the water. So very easily you can take a conductivity measurement, convert it to total dissolved solids, and you kind of know whether or not your water is conductive or not. But dissolved oxygen is a little bit more of a complicated matter, and most people don't measure dissolved oxygen.
I think you'd have to go to a lab for something like that.
Right. Right. That's a good question.
All right.
Okay.
Anybody else got a question or comment? Yep, we got another one. Hang on.
We do have one here. This one came from Bob Kessner. He said, we currently use Fernox F1 protectant with estimation of concentration. Does this compete with or complement Caleffi's water treatment cart? I'm concerned that we can't know the fluid quality with our current methods versus potential ongoing water quality check potential using the Caleffi cart. Does the cart treated water help keep valves from sticking or degrading?
It's a good question, and it involves total dissolved solids we see on the graph here. So the Caleffi cart that's being referred to is a product demineralizer. Caleffi offers it in the marketplace. There's a number of other folks that have demineralizers. I'll name a couple of them. Watts Water as an example. We have Axiom, all good companies that offer this type of product. And basically, the demineralizer takes water that has dissolved solids or minerals in solution, and therefore is conductive, and makes the water unconductive. And so the answer to that question is yes, the use of chemicals is very compatible to demineralized water. In fact, most chemical manufacturers are not shy, but I would say they don't like to mix their chemicals with water that has large quantities of any type of dissolved minerals, especially minerals such as nitrates and chlorides and stuff that can cause the chemical to come out of solution and form that sludge that we talked about in an earlier slide. So absolutely yes, demineralized water is very compatible with any type of conditioner out there.
And I read an interesting German study here recently, and they look at water two different ways, or fluid, whatever it might be, and they say the water outside the system can be dealt with before you put it in, run it through like the Caleffi demineralizer, and fix the water before you put it in there. Or once it's in a system, they look at a chemical as another option, because then you can fix water that you put in that wasn't in spec by putting, the conditioner chemicals, the oxygen scavengers, the buffers, and stuff like that. So we're of the opinion that you should start with a good quality water, and then if you feel that you do need additional protection, certainly with the glycols you'd want to do that too, then you could go to some chemicals. Just know that, with the chemicals, you've got to maintain them and keep working on, and you've got a chemical romance that you got to deal with until you end that romance, basically. So water outside the system, water inside the system. The key is knowing, when you've got problematic water, and then we're here to help you fix that. So,
Bob, can I admit something? When this slide got put in, we thought it was sourced from a water quality standard in Europe, such as Germany. And late last night, I was doing some reading, and I uncovered the same graph used in Axioms literature, good education literature. And so if it was Axioms, well, thank you. We borrowed it, but I think you guys did a good job with explaining this.
We've got some other questions, a lot of questions coming in that are typed in here, though.
Okay.
Let me back up. First one was, what is your experience with an electronic scale buster in a closed system? That was from Vincent Monaco. Any experience with that, Bob?
Well, I know they're out there, and there's a lot of controversy around those, whether you're putting magnets on your pipe on a couple places, or wrapping wires around, plugging in the wall. I'm not an expert on that. I mean, obviously the people that are promoting those and selling them are showing examples of look what it did to the system. What I understand about those is they don't, obviously they can't take the minerals out of water. Where would they go? It's a closed loop system. They're not coming through the wall of the pipe. So as I understand it, they can keep minerals in suspension so that they don't coat up, that they don't, scale out the components in the system. But again, I'm certainly not an expert on that technology, but I know it's out there and it's being promoted pretty heavily by a couple companies as an option to fixing bad water, especially limescale problems like that, either domestic or boiler systems. So
there might be somebody on the phone that's part of that business, and I'd have to say we haven't seen any studies, third-party studies that would indicate a magnetic type of approach for scale removal or scale prevention is effective. Now, that's what the caveat is, that we haven't seen anything. Perhaps there is some out there, and anyone that knows of it on the phone, you can send it to us. Because, Kevin, I think maybe from time to time we do get that question about that type of way of
fixing water,
preventing scale or fixing scale.
Yeah, we may have, we don't have a good answer for that right now. If anybody has anything they can chime in, that'd be great.
Now, that being said, there are electronic anode rods that, but they're cheap to send out with their indirect tanks. I know you can buy those on the market, where if you've got a job where the water is eating up your anode rods in a domestic water system, they have electronic. I don't know if that's what you're referring to. They do have electronic anode rods that deal with that don't get consumed. So we'll try and find out more about that. So let's see. We've got a couple other, we're getting more typing questions than hand raised, but we want to. Yeah, let's take a couple questions on that.
First one is, does the type of dissolved solid matter? What are the main types to check for? And that came from Kyle Mansky.
Maybe I can grab that one. Does the type of dissolved solids matter? When the industry refers to total dissolved solids, they're referring to the content of minerals that have dissolved by water and have gone into solution, thereby creating ions, both cations and anions, positive and negative ions. And this is what gives water its conductive properties. Now, to the extent that the question is about conductivity, the answer is all dissolved minerals will create conductivity, whether it's calcium or bicarbonate or chloride, sodium, potassium. They all will create electrically conductive water and thus make the water capable of completing the battery cell effect that is the basis of corrosion. Now, are all the same? From a total standpoint, I told you about electrical, but from a scaling standpoint, They are not all the same, and in a few slides we're going to get to scaling and explain that, and what are those issues concerning scaling.
Yeah. Now the TDS meter that we offer, it's going to read all. It won't break it out and say, well, you've got so many parts of this and so many. You'd have to send it in for a pretty thorough analysis to break out exactly what's in that TDS number. If you got a high TDS number, say, well, can I just fix chlorides, or can I just take the salt out, or whatever? You'd have to send that off to sample. But what we want to do is get it all out. We don't really care specifically what it is. We just want to get that number low enough that it meets the boiler spec, that it's not going to affect the boilers, the pumps, the components that we manufacture and sell. So should we keep going here? Another question on that, or what do you think, Mark?
Yeah, we have more questions coming in. Pete the Heat asked, what is the ideal pH range to start with?
The pH to start with in terms of starting up the system? Okay. The ideal pH to start with, if you read read the manufacturer's literature, it depends on the type of metals used in the system, but a range of 7.5 to 8 you'll see cited quite a bit, because in order to minimize corrosion, water is ideally should be slightly basic, north of 7. And so 7.5 to 8. Now most systems on their own, even if they start high of 8 or even low of 8, will tend to stabilize. So if they start at 6, what happens in terms of chemical reactions in the system is they'll start migrating up. And a number that you'll see in literature would be a number of 8.2 commonly cited, that hydronic heating systems on their own will tend to migrate towards 8. Okay, so if you look at the German water quality standard, they cite 8.2 in other literature. Now our empirical evidence of testing here at Caleffi, what happens to pH, I think even recently we tested a system that the pH, once the demineralized water was put in the system and it started up at a low pH, migrated up over the course of time. Is that right, Kevin?
Yeah, it stabilized. Tend to stabilize. I have an example of a system that was installed 16 months ago, and that happens to be my personal hydronic system, but it's about, I have about 2,000 feet of oxygen barrier PEX, and just a standard, couple of cast iron pumps. I used city water that we measured at 358 parts per million, which is 21 grains, which is going to be higher than a typical boiler spec. And the pH was 8, so that was my city water supply. And when we filled the system with the Caleffi demineralizer, coming out of the demineralizer, the ppm was really low. It was just in the single digits, and the pH was a little bit low at 6. So since then, the pH stabilized. In fact, the pH stabilized right away. Within a day or two, it went to 7 and continually stayed right around 7 to 7.5 over the time. So it did stabilize, and the ppm creeped up as we would expect. And we just tested it last night after 16 months, and the ppm is stabilized right around 50, which is about 3 grains. So that's over a year, and that's just pure demineralized water put in a very typical common system. So the pH seems to seek, seek Mother Nature's balance in this system. So there's no chemicals in it at all, and it's been a pretty good experiment for us.
Yeah, and that's going to. We'll get to glycol. That Pete, I know some of your systems use glycol for snow melt and stuff like that. The pH is going to be different when we get to that. So hang in there. We'll talk about the effect of pH and glycol. So you want to do another question?
Sure.
We're halfway into it. We've got time.
Sure. Bill Gable also asked, what about using RO water?
Okay. Very good question. What about using RO water? Well, there are various methods available to the installer or the engineer to take out the dissolved minerals, or what's referred to as deionize the water. That's the term, deionize the water. And there's really 3 methods that one could use, and one is RO. That removes, to a large degree, dissolved minerals. Distilled water, so you can use water that has, go to the store and buy water out of the jug that has been distilled. And then you can also, thirdly, take out the minerals by way of mixed bed media through ion exchange, which is the process cited by myself concerning our CART and Axioms and a number of others now in the North American marketplace. They all produce very low conductive water. RO might be 5 parts per million coming out of a typical RO, distilled a little bit purer yet, 0.5 parts per million, and demineralized water pretty close to 0. It's probably the one that's going to be taken out the most. However, all of those would be fine because, as we show on this chart, anything south of 40 parts per million is going to substantially eliminate any chance for corrosion, even if you do have oxygen ingress. Okay, so the question then becomes cost. How much cost per gallon does it take to use any one of those methods? And whether you rent it or buy something that does that, it becomes the math exercise that the contractor has to take into consideration. But it's a very good question, but it's one we get often. All 3 methods produce deionized water, just at slightly different concentration levels, but they're all perfectly fine for corrosion prevention.
And RO, typically, if you're talking like a residential size RO, I mean, you could take all day to get a gallon of RO water in that little container below there, and it might use 3 to 5 gallons to do it. So there's quite a bit of wastewater that goes down the drain as it squeezes through that semi-permeable membrane. So it's not fast, and it's going to be expensive, and it might, not be realistic if you need hundreds of gallons, for example, to fill your system. And the same thing with distilled water. True distilled water is made by boiling the water, collecting the condensate on the stainless steel thing, and dripping it in the bottle. So as you can imagine, that's pretty slow and expensive. Now, another ion exchange is the water softener. We're going to get to that too, because that is a resin media bed with an ion exchange. But there's something to know about that, which we're going to get to next too. So that's another good. One more?
Yeah, let's do one more. Actually, I have a question from Mike Levesque, and I'm going to put.
You got about 20 questions.
Yeah, I got a lot of questions. I'm going to put Mike live. So, Mike, hopefully you're ready to go. So you are unmuted, Mike.
Okay, can you hear me? Okay.
Hey, we got a live person. Thanks, Mike.
Yeah. So the question I have is, it seems like we have some fixes for total dissolved solids. And I didn't know if the fix for dissolved oxygen would be, a good Caleffi air separator.
That's a good question. Okay, so looking at this chart again, and thanks for the question. If you have a high level of oxygen, dissolved oxygen concentration in your system before you start up, let's say, all right? Let's say it's off the charts high, all right? What happens through the process of putting a high-performance separator properly placed is that that water is going to either undergo a pressure reduction, which will bring it out of solution in the form of non-dissolved air, or the temperature will be heated up, such as coming off of a boiler, creating microbubbles. And as a result, air separators scrub the water of dissolved oxygen this way. And through the repeated cycles of water going through the process, getting boiled, coming out, or it could be even a heat pump, quite frankly, you do scrub the water, and your dissolved oxygen starts to migrate down. Now, even at that, until you heat the water substantially, the dissolved oxygen content is probably somewhere going to be north of 0.10, as you see in the chart here, all right? But what happens with dissolved oxygen that's not emitted from a system is that the process of oxygen coming in contact with metals in the system creates a natural, call it healthy corrosion on the surface of all the metals. In the case of iron or steel, it would be magnetite or hematite. Magnetite, we'll get into that later, is the preferred method. You get aluminum oxide, you get cupric oxide on copper. So those all become, and those consume the dissolved oxygen. So just by nature of the system operating, oxygen starts to deplete in the system. Then it becomes a question, once it's depleted largely, is does your air separation performance and your pressure management in the system, is it sufficient enough to be at a level greater than any rate of ingress? And I think, Kevin, you talked about yours as a non-oxygen barrier PEC system at your home, but there's many places that you can get oxygen ingress, especially with the increased use of polymers in our piping these days, right? You got high-density polyethylene geothermal loops, you have PPR, you have PEX, and the like. Good question. High-performing coalescing type air separator, I think, is the de facto state-of-the-art in the industry today, I think. Bob, would you concur?
Yeah.
And you got ours, and you got a number of other good brands out there of coalescing that does a good job getting that oxygen level down.
And just make sure they work. That's key to that. Sometimes on some of the chat rooms, people say, "Oh, I spent all this money on a high-performance, air separator, and they're plugged up. They're not working." I know later in the picture we might have some pictures of some that plugged up. I mean, you got it in there, but it's not doing its job. But the other thing is that oxygen can get into a system, and even on barrier texing, oxygen gets through that at a low rate, but over a period of time, maybe 5 or 10 years, especially on the higher temperature systems, you still have oxygen getting through the wall of that tubing. So it needs to be, again, the numbers that you look at when we show you our tester here will indicate if that's happening. If you get a lot of oxygen in the system, it's going to show up in a number. You say, well, I either got to put an oxygen scavenger in there to treat that, or keep it out of there. It's coming in through an air vent or a pump seal or something like that. So.
Hey, Bob, this is Jody speaking. The other one to consider on this is, control leakage. Because for every gallon of water that exits, a gallon of water has to come back in, and there's a good chance that water coming in is going to be oxygen and air saturated. So this can actually, depending on how tight your system is, this can be a very significant factor in the continuing injection of oxygen into the system.
Faster than it can be consumed on a big commercial job where there's a lot of leaking seals or air vents. That's a good point.
We're getting a lot of questions basically related to the resin and that product. So I don't know if we want to address those now.
Yeah, there's no more on this because again, we don't want to ignore anybody here, but we'll move on to another topic, and at the end we'll open it up again if we have some time, and if it has to go into next month, we'll certainly do that. But we had a few that we want to get to just to trigger all the points that we want to get across today. But if we have to come back to a question,
I think, Bob, we get to the resin, as Mike mentioned, in about 6 or 7 slides. So I think we'll get there.
We'll get to that.
Okay.
All right.
Mm-hmm.
Okay. So we'll lower the hands. Okay.
Okay. Here we go. All right. Lime scaling. This is everybody knows what that white deposit you see on the inside or the outside of pipe. So this is the scale. Mary's got up there now. Gives you an idea of the scale thickness and how it penalizes your heat transfer. And there on the side, you can see what 1 millimeter is on that little day planner calculator that Mark's showing you there. So it doesn't take much, and it doesn't take long to get that kind of buildup if you're putting water in that has a high hardness lime scale in it. So if you're selling your customer high efficiency equipment and you're putting this type of water in there, you can see what kind of penalty you're taking. That's going to show up in operating costs of that equipment, and certainly longevity of it. If you start putting hot spots on that heat exchange surface, that's where you burn through. That's where you get problems with pinholes and boilers failing. So anything else on that, Mark?
Well, it sounds like everyone has a pretty good grip of that because they rated lime scaling number one.
Yeah, everybody's. Right? I mean, if you're a plumber and you drain water heaters, you've certainly seen lime scale and understand what that does to your system and your performance and the noise it makes and everything else. So yeah, this one is this should be well known to everybody else.
Let's put it in the next slide, and I think maybe Jody's going to make some comments on it.
Yeah, so these are Jody's pictures.
Can we jump back a slide? Yeah, so you look at that 1 millimeter. That's really not a lot of lime scale buildup. 10%. That's less, as Bob said, less heat going in to the building. More losses. And the other thing to consider is if this energy is not going into the building, typically you're going to see an elevated stack temperature and possible problems there as well. And this is during normal operation where there's no failure of the boiler. So if we jump to the next slide. Two great pictures showing a condensing and a non-condensing boiler, and both of these you can see have a very major lime scale issue. The non-condensing boiler on the right-hand side, that actually is my hand in the picture, very large buildup. It's almost like a granite in there, and that material will significantly reduce the heat transfer through and without when there the boiler cracked because of thermal stresses. On the left-hand side, the condensing boiler, a little bit different. And there you'll notice a lot of it's just built up and is sitting on that plate. The boiler itself, because of expansion contraction, as it built up, it was flaking off. And here, the problem was a flow condition. All of that material started to choke the flow through, causing the performance off. Now, Mike, are we getting any lime scale questions coming in yet?
Oh, we lost Mike for a second. He'll be back. But that, I mean, that's more than 1 millimeter, obviously, on the right-hand picture. But you can see where it flakes off the water tubes in that boiler. Like Jody says, that that boiler heats up when the burner comes on, that metal expands and it releases that, and it falls down to the bottom of that plate on that, the head plate on that boiler.
Jody, we did have a question about the resin in our system. Is the resin balanced so that it will extract all common minerals found in domestic municipality water sources?
Yeah, I think that's about 3 slides from right now. So if we want to jump to the next one.
Yeah, next one's going to be a poll question, which is perfect for I think the questions that are coming in here. So let's go ahead and
run this poll question.
Let's run this poll question.
One choice of how you would.
So this is another one if you only had one choice. If your water was hard, so you have the choice now of putting hard water into your system, how would you limit its scaling capability? Would you, A, use a chemical to sequester the hardness? Would you choose to soften the water typically? Would you decide to remove the dissolved minerals? Or would you control the pH from drifting high? Or would you minimize the heat exchanger surface temperature? Now, all of those do reduce scaling, but which one would you choose? Some are more effective than others.
Yeah,
so let's go ahead.
I can answer that. Oh, we're getting some good response there. Okay.
Okay. So we have, interesting, so removing the dissolved minerals, okay, number 1. Softening the water, number 2. Chemical sequester, number 3, and I think probably, guys, this is something we probably expect along these lines, right? Okay. So removing the dissolved minerals would be the first choice. Okay. So let's then with that go to
how a water softener works. So this,
well, is there a question? Okay, let's go to the next.
Yeah, let's talk about this, then we'll open you up again.
Okay. Well, the second choice was water softening, which uses typically ion exchange technology. Basically, the resin is a positively charged resin that removes positively charged with sodium on the beads, and so it removes minerals in solution, specifically calcium and magnesium, those that contribute to lime scaling. But what happens is that as the magnesium and calcium gets captured, and to a very small degree iron, they get captured, but in exchange, the sodium gets kicked off and ends up going into your water. So the sodium content increases inside your water. That's why when you taste water through a water softener, it has that sodium taste to it. Some people will bypass, like this installation, and use unsoftened water for drinking water. Back to the topic, though. Now you have a, depending on how hard the water, you have water that now has a high concentration of sodium, okay? So when heated, as a result, sodium hydroxide can form, and it's also related to the carbon dioxide coming out of solution in the system, forming sodium hydroxide, okay? Resulting in the pH can rise. In fact, it can rise above 10. And that might not be a problem for many systems. However, if your system has aluminum, aluminum doesn't like to have typically a pH anything higher than 8.5, to that earlier point. So the bottom line here is that if you have aluminum in your system, it could be a fan coil. A lot of fan coils will have their coils made out of aluminum and other parts, or an air handler,
or a boiler,
or some aluminum boilers, right?
Yeah.
All right, that's especially problematic, especially if your water in your system has chlorides. Now we're finding more and more well water tested to have what? Chlorides. Because quite frankly, when you do the backwash on your water softener, you're basically dumping chlorides out to perhaps your septic system, right? And that can leach down into your aquifer. So bottom line is, be careful with water softening, all right, when you are looking to make the water from scaling. It does do a great job preventing water from scaling. It can prevent scaling to a very large degree, if not completely eliminates it. But you got the issue of this potential corrosion issue.
Some people say that the lesser of two evils. If you've got water that the hardness is off the scale, and like many places do in the U.S. now, are you better to do this and use the softened water to put in there than putting water that might be 100 grains hard or something like that? Well, just know that you're substituting one lesser problem for still another problem. So there's a better way to do it that's very similar to what a water softener is, and you eliminate all that potential problem. And the other thing you'll find with water softener is, if you use it on domestic water, that's when you start seeing those green or blue stains around the drains on your sinks and around the bubble aerators on your faucets. That's because of that, that softened water is causing that reaction. So you can cause other problems. So let's, is there anything else on question mark? Keep rolling.
No, I think it's a good point. It was a good question. So softening water is a good, effective way of eliminating.
Yeah. So
there was two questions about how do you eliminate limescale buildup, especially in indirect heaters. There was also a comment by Richard Graves about mentioning VDI 2035, which states based on European agency regulations, it's illegal to use regular domestic water in a heating system.
Yeah, thanks, Richard Heatmeister, who's from Germany. He mentions that German standard, which that VDI is actually the German equivalent of ASHRAE. It's a membership of engineers over there, and they put together a really good comprehensive water standard. And in fact, we've got it in our slides. If we get that far, we're kind of running long here, but we did post that up there, and thanks for reminding us on that. So.
It was also, I'm sorry, okay. There's also a question about, ion exchange. Doesn't it just switch the hard water ions for the sodium ion?
That's a water softener.
It's a water softener, correct. That's a water softener.
Right, that's backing up. That's what we just talked about, ion exchange. But it's only exchanging positively charged ions. Any negatively charged ions in your well water, such as chlorides, sulfates, phosphates, carbonates, bicarbonates, those will all pass straight through. So if you got chloride in your groundwater and you go run it through a water softener, the chloride's going to go right into your water, right into your system. Yeah. And if you got stainless steel, that's also a big issue. Yeah. Stainless steel does not like chlorides.
And somebody backing up, somebody said an indirect water heater. Now, you might want to soften the water going to the water side, the domestic water side of that indirect heater, so you don't fill that up with scale. Just know, again, if you're using the stainless steel indirect tank, that that level of those chloride and the sodium is going up in that. Now, and the other thing, I was just thinking about that. I lost my thought here, but let's.
Well, I think that you got a couple of questions that will best serve probably with this slide right here, because questions are concerning getting rid of minerals in solution other than the hard minerals. And so here we have a photograph. Does anyone want to talk about this particular slide from Michigan on a demineralizer?
Yeah, and I'm not 100% sure what he's doing here. It looks like he's going through our demineralizer, and then I don't know why he's going through those little totes, those 5-gallon totes. What we're assuming is he's trying to measure how much water he's then going to our flush and fill cart to pump it into a system. And we're thinking maybe he's blending glycol, where he's putting so many gallons of water in with so many gallons of glycol behind it, because it looks like he's got one too many steps here to get water from the deionizer into the system. But I mean, that's what he's doing, is he's running all the water that's going into that system through the Caleffi demineralizer there. So he's stripping out the positive and negatives. He's taking that water down to a pretty pure state by going through the demineralizer first, and then obviously pumping it into the system here. So if you've got this is what I was going to say, if you've got our hydronics that we did on our call, we've got a really good graphic as well as an explanation of the difference between softened water and demineralized water with those little bubbles and stuff, if some of you folks have looked at that. If not, certainly review that after this, because we can't cover everything in this time we have here, but that does really do a good job of explaining the big difference between softened water and demineralized water.
Well, some questions are coming in relative to how do I get rid of minerals other than calcium and magnesium that are problematic, and the answer to that is what you're looking at here is the demineralizer. That's why these guys went to this pain of having a demineralizer. They could take site water, which is typically pretty much almost free, right? And they can treat it. And regardless of what minerals are in solution from your site water, the demineralizer is going to remove it through ion exchange. So unlike a water softener, which only gets rid of largely calcium and magnesium in exchange for sodium, A demineralizer gets rid of all dissolved minerals in solution, including chlorides, sulfates, phosphates, iron, calcium, all of those problematic ones get, in exchange, produces water. And that, to your point, Bob, we explained that more fully in the Hydronics number 18 in terms of the water chemistry. So this contractor is producing good water from bad water, storing in these totes, and then pumping it into the system. Looks like you're making a premixed glycol or something like that.
Yeah. Now, the other side of that is when you do that with a demineralizer, you can no longer do the sodium exchange and wash it out. It has to be washed out with a lye or real caustic solution. So it's not something that you can regenerate this type of a resin bed on the job. You'll have to, replace the resin in there basically. But that's because it's scrubbing both sides, the cations and the anions out, that you can't or won't do with a softener. So, all right?
Okay.
I'm going to do another.
A couple more slides here.
Yeah, we have a few more here, but that's me. Hi. In fact, that's at Kevin's, the system that we just talked about earlier out of Kevin's house, where we put it in last October, I guess we filled that system for the first time. So it's just an example how you would pipe it in with a double valve there. We can just flow on one side, pick it up the other. So, and the bags that you replace once it's been consumed, the resin's there on the lower right. So keep going here. Oh, here's the bubble. I didn't know it was in the slide. So there's Mark was talking this a really good graphic of the difference between your bad water on the very left there with all the different colors, the positive and negatives in the bubble there. And you can see after the softened water, we've taken some of them out. You can see by the colors that we've taken out, but we've left an awful lot behind in that bubble. And then on the very far right, we've taken both the positive and negatives, the cations and anions out, and ended up with pretty much pure water. I mean, that's it in a nutshell, the difference between softening and demineralizing the water. Anything you want to add to that? Other questions or anything on that, Mike?
No, actually, Luke Landry, he's had his hand up for a while here. Sorry about that, Luke. If you're still ready, I can put you on live here. So.
Come on, Luke, talk to us.
Okay, Luke, you should be live.
Yes.
Hear you. Yep.
You hear me?
Hey.
Okay.
Yep.
Going back to your hydrofill there, can we use that to demineralize water that's already in the system, or you have to use the new water that you're putting in?
Yeah, and we show that in Hydronics how you can use it as like a bypass filter and do that. Just be aware that you can't do it with hot water, under 140 temperature, because you'll start reducing the effectiveness of the resin. So you'd have to do that if it's a boiler system. You'd have to do it when the system's cold or off or not firing up. So, and also, you'd have to make sure that a portion of it goes through there and a portion of it bypasses. It couldn't, in this example here, we couldn't do an 1.25 inch flow right through that. And the meter on the top of the hydrofill cart there has a TDS meter on it. It'll tell you when your resin's being consumed and when it's time to replenish the bag. So yeah, and certainly on a big, let's say you got a commercial building, you don't want to drain that whole building down and get rid of that water and start all over. You're going to have to bleed that system. You could spend a lot of time there. So you would just run this as a bypass filter. And this valve that we're showing could do that, where you could allow, you can see the big valve in the center. You could slow that flow down and let it go down through the filter and back into the system and adjust the and this is a valve that we offer. There's other valves like that out there. I call it a three-purpose valve, where that's the flow going through it, and that's where you can regulate what goes in and out of it. And then over here on the top, right here, is where the meter is. You would watch the the TDS level, the fluid going into the system. So yeah, that's a good question, and yeah, it's possible.
What happens if the ones
One of the other things I probably would do is I would also put some sort of pre-filter on there. There is a very fine mesh screen on the top and the bottom to make sure that the resin stays inside it in case the bags rip open. I forget, maybe Mark or Kevin knows how fine that mesh is, what the particle is, but I probably pre-filter just to make sure it doesn't trap whatever's out in the system.
Yeah, that's something to watch for. You want to put fairly clean water into the demineralizer. You don't want to let a bunch of particulates go in the entrance and the bottom.
You know, so it looks like I mean, we'll keep going here. I know we're at over the time limit actually, so if we'll watch the count of people on here. We've still got a lot of people on, so we'll keep going a little bit more because we didn't get but 2/3 of the way through this. So if you want to hang in there, great. And then we'll consider after we end here if we should do this again next month and pick up where we're going to.
Before we do that, can I comment on Luke's, because we do get that question. Many installers will want to, in order to purge the air, all right, if you're limited by the flow rate limitation of sending water through the demineralizer and directly into your system, there is a, 6 gallons per minute or something, I think dissolve is pushed through there, right? Or,
It's higher for the large unit.
okay, for the larger unit, but people like this really purge the air ahead of the water, get it completely rid of air. So given that, that's the perfect time to, as Luke asked, use kind of that approach where you just basically create a differential and just kind of keep scrubbing the water. Yep. And there's no problem with sending water repeatedly through a demineralizer. It doesn't have to be a one pass, right? It's just going to keep scrubbing and scrubbing and scrubbing until you measure that the TDS or the conductivity is to where you want.
Yeah. All right. Anything else, Mike, or should we move on here?
We can move on.
All right. Oh, chemical additives. Another poll question. Yeah, we're into this halfway. I think we're going to take this to a two-part here because. So, what do you want to run this poll question? If you can hear us on the chemical additives.
Okay, so I'll read it. In your experience, what is most important to ensure ongoing chemical performance? So, ongoing meaning that the chemicals are doing their job on an ongoing basis. So, what do you consider to be things most important? Check the pH or TDS routinely. Disregard the second answer because it's just repeated, I think. So, and then, or do you make sure to check for sludge or debris formation regularly as an indicator if things are hunky-dory? Chemicals, or you might have the attitude that chemicals don't require maintaining these days. Just dump it and you're good to go. Or, and I say these days, it could be because of the quality of the chemical. Or I don't use chemical additives. So you got 4 options here, so give it a thought. And again, we're kind of forcing you to choose one just to see what you prioritize.
The first 2. All right, this is looking good. We can kind of see them as they come in. There you go.
Okay.
70%.
Yeah,
70%.
Check pH or TDS routinely.
Yeah, you're right. That's a good answer. If you add the top 2 lines, you come up to what 70% there. So that's certainly the easiest thing to do. I mean, how would you check for sludge unless you open some low point of the system to see if it's settling down there? So, I mean, the meter that we have or that you can get can check the water. You know, take a sample really anywhere out of the system and see where you're at there. So.
Hey, Bob, a point about checking TDS though regularly, if they're referring to also TDS. Many chemicals will actually they're actually mineral based, and so when you put them in your system, if you measure the conductivity of your system before putting the minerals in, let's call it 200 parts per million TDS, and then you put an inhibitor of some sort or some type of chemical, what happens? It changes the conductivity.
Yes.
So it jumps,
yeah.
Because chemicals, unless they're completely organic based, which they usually are not, will raise the TDS readings, okay?
Yeah.
So it's important that that be known so that that becomes your base, so that as ongoing you check pH and TDS against the known base.
And I think what you'll find from the chemical people is once you start using their chemicals in there, they want you to maintain that with their tester, their test kit, though, you know, usually comes with the big quantities of it. They say, okay, sample it once a year, once every 2 years, and kind of keep an eye on it. But if you use their test kit, it's going to tell you specifically when there's a boost that might be required for that chemical instead of, you know, just a generic reading of the water. And here are just some examples of how you could add chemicals into a system. You know, a pot feeder, you can see the top of that feeder on the left comes off, and you could dump your mixture in there, and then, you know, pull it into the system. This came from a UK website with open systems over there. I guess you can just open a radiator cock and dump it in if you're up high enough, or certainly with a aerosol can where you can eject it. A lot of the chemical companies are making it easy for you guys to inject it in by just giving you a can that's got a little you know, hose connection on it that you can just screw onto a male garden hose thread and pull the trigger, and it squirts both the cleaner as well as the inhibitor chemical in.
Okay.
Go ahead.
Hey, Luke, are you still there?
We got Luke back.
Yeah.
Okay. Yeah, I saw that you had sent in a question, and if you wanted to ask that live here.
Yeah, I just wanted to know if we're using chemical inhibitors, like for example molybdic in the system, and we use the hydrofill. Does the resin in the hydrofill remove the corrosion inhibitors?
Molly's. Yeah. Yeah, it's going to pull out the good stuff that you're putting in there, which is probably expensive. So you'd want to, fix your water, clean up your water before you start putting your chemicals in. Otherwise, if you do run it through the demineralizer, you're pulling those chemicals out, putting them in the resin bead, and putting good money after bad, I guess.
Yeah, and that's a really good point, because if you choose the method of filling your system, conditioning it, and then using the demineralizer to take the conductivity down and your hardness out, you're pulling also your inhibitors out,
good stuff
because they've gone in the solution and they've ionized.
Yeah.
And now the resin is going to basically capture it.
And that goes back to that German study I read where they said, fix the water on the outside before you put it in. Watch your system if you want to add chemicals for additional protection or freeze protection or whatever. After you put the good water in, it's the time to consider that. So,
yep.
All right, so what we got here? So, again, with the chemicals, now we're talking about cleaning agents. I mean, most of what these cleaning agents are is they're soaps, they're detergents that go in there and they break up any oil, any grease, any solder flux, anything that might be in there. And then you purge that out, you wash all the bad stuff out, and then you put in your good water, and then look at your water and see if it needs to be adjusted or boosted, and pH, either up or down, depending on what it might need. We're the opinion, if you've got a good clean system, whether it's a new system or an old system, that just putting good water in there, demineralized water, should be the final step. Now, some people choose to go a little bit further and put a conditioner that might have a film provider, might have some other stuff. If they think they've got a loose system as far as some O2 getting in or something like that, they want that extra level of protection. That's what we feel you can provide with a chemical additive to it. So, but again, now you've got to maintain that with their test kit to know that when you need to go back and boost that chemical that you put in there with a boost kit, because you've consumed the scavengers or the buffers that are in there. So anything.
Well, I think it's a good point. I guess a couple of clarifications, just going to emphasize some points. Back on the cleaning agents, we've found when someone has cleaned their system and but didn't completely get rid of the cleaning agents from the system before they filled it and conditioned it with inhibitors, the inhibitors will react with the cleaning agents in some cases, especially if they're from different companies, and they will cause the inhibitor to end up degrading.
Or maybe foaming or something like that. If it was soap that was
foaming or something like that, and so that's usually a tale of needing to get the cleaning agents out of there, right?
Yeah.
So that's very important. Then the conditioners and inhibitors have a chance to work as properly if they're chosen to be used. Okay. Now, before we leave this slide here about adjust pH up or down, and that might be an example where, as we mentioned, if you have aluminum in your system and you have softened water, well, you could have your pH start to drive up above where aluminum doesn't like to live, and so you might want to have a pH reducer. Okay, and then the buffer is basically adding alkaline to it to make sure the pH doesn't change very much. It basically kind of helps lock it in, right? Yeah. That's what alkalinizers do. They're buffers of pH. And O2 scavengers, we talked about that. Depending on the type of O2, we're of the opinion you really shouldn't be using O2 scavengers because you should be doing air separation and getting rid of the oxygen by way of that means, rather than put a scavenger in there that could end up precipitating, creating that sludge that we talked about early on. But perhaps some of the chemical manufacturers could differ against that with perhaps their product. And then film providers. I think film providers, if people don't know what they are, they're a corrosion inhibitor, right? Is that what they would be called? But they create a barrier of electrical conductivity between the fluid and the metal by establishing a 1 or 2 mil thick, call it, I won't say oily surface, but basically an insulation surface, right? but they have to be properly dosed, because if you underdose, what have you done? If you underdose and you don't thoroughly coat your system of the inhibitor, and you leave some spots that didn't get coated, they become, call it the sacrificial lamb. They're equivalent to the anode rod inside your hot water heater. All right, they're going to receive the full corrosion potential of the system. Now remember, you just increased the conductivity by putting additives into it. So not only have you laid bare some parts of the system that can corrode, but you've also increased the conductivity. So where are you going to get problems? You're going to get corrosion in those. So underdosing is an issue, and overdosing is also an issue. And I think, who was it? Pete DeHeat mentioned BDI 2035. I think we get into that, but they say be careful about overdosing if you do choose the chemicals, because you can get microbial film build up on and then that becomes a harbor for bacteria growth, and that ends up potentially in bacteria corrosion, induced corrosion.
Food source.
Yeah.
A couple of questions on how often to check the pH. I don't know if we mentioned that.
Well, I mean, I'd certainly check it, after you first fill up a system within maybe that heating season. I would check it at the end of that heating season, and then, maybe start yearly, and if it isn't moving around much, maybe go to every 2 years. I know with glycol, that's important to catch it before it goes too bad, because it'll start attacking things. But, I mean, if it's not moving, like Kevin's, isn't moving around much, I don't know that he has to check that every time you go in the basement anymore like you've been. So it just depends if it's moving around. If it's moving around, I would keep an eye on it and figure out why it's moving around and fix that problem that's causing it to make big jumps either up or down. Something's caused that pH to move. And again, it could be oxygen getting in there. It could be something that was left in the system. So what do we got here? 117. You want to go another 10 or 15 minutes here?
Yeah, I think we should go to 90 minutes.
Yeah, we said 90 minutes. We'll keep going here. So that's the key to, your chemical romance, is you got to call her up once in a while. Or him. All right, what do we got? I think we got another poll question coming up here. All right.
So if you use chemicals, what best describes the most important reason why you use chemicals? So we've heard some questions about using them, but not why you use them. So do you use chemicals typically only to fix bad water? Do you always add chemicals, whether it's a new install or a retrofit? Do you consider chemicals only if problems arise? And lastly, do you add chemicals in order to conform to the equipment the specs of an equipment manufacturer or equipment manufacturers? Okay. Yeah. So again, we're forcing into letting us know, and maybe the rest of the audience know, why people choose to use additives. So let's go ahead and
a lot of participation on this one. All right.
So go ahead and
let us have it, Woody. Let's see there we go.
Okay. So we have a 46% that always add chemicals. Okay. They add to conform to equipment manufacturers' specs. Only fix it with bad water, and only if problems arise. So I think, Bob, since we only have 10 minutes here, maybe we can agree that in April, where we have an opening for a webinar topic that we have to decide, maybe we do a part 2 here, because we got a lot of questions and we still got a lot of material to go over. So maybe we can go back to the poll results. Did we have that poll? I guess the question would be, for the people many people that answered, okay, right here. When a large share answered when needed to conform to equipment manufacturer's specs. So that, I guess the question would be, what specs specifically of a manufacturer's equipment does the chemical use allow you to conform to? And I suppose the issue is warranty and long lasting. But is there anyone that would be willing to weigh in on this as to why and what conditions, or what is it about equipment manufacturer's spec that the additives will help you conform to? Anyone raising their hand, Mike?
No, not yet.
I'm going to pull up the boiler spec.
Yeah.
All right, let's show you. We pulled some boiler specs right out of their manuals here, and we'll show you what they're asking you to do here. So Jody might weigh in on this. I think you pulled some of these out of different manufacturers' I&O manuals. So Jody's still out there.
Jody, you're on mute if you're out there.
Yeah. But see what you'll notice in this is all the ppms, parts per million, and again, this is what you're going to read with that TDS meter. Now let's use the upper left one there for an example. You know, they're saying so many parts per million, calcium, magnesium, and stuff. The TDS meter isn't going to tell you, isn't going to break that down.
Am I back on?
Oh, there you go.
Yeah,
okay.
there you go.
Yeah, we're just talking about these.
Yeah, for some reason I've been muted. And really, when you look here, the thing to remember with these are they're boiler specific. Really doesn't talk about the rest of the equipment in the system. But I always like these because it really points out that that softening isn't the solution. Because everybody will usually list some requirement of water hardness, but more and more, particularly if you look at that one that's up in the left-hand corner, it's calcium and magnesium and total hardness, which you look at that and a water softener can address, but the chlorides and the sulfates, since they carry a negative charge, they're not going to be even. They're just going to blow right through the softener, never get touched. And you look around there, and then the next one below has chlorides as well. The one to the right-hand side, again, chlorine concentration not less than 200 ppm. Another one that typically shows up, and I didn't have one on one of these, but nitrates as well. Chlorides, sulfates, nitrates, they're all going to attack, particularly a stainless steel boiler. So we start to look at the water treatment and particularly the need for the hydrofill. The hydrofill pretty much addresses everything that's listed there as a potential water quality issue from the boiler.
Yeah, and there's that pH level that Mark was talking about earlier. This one happens to be 8.5, but the range is, as you can see, pretty tight there. That's 6.6 to 8.5. So.
If you go off to the right-hand side, the bigger block, pH between 6.5 and 9.5.
Yeah.
Now, Jody, the poll question resulted in a pretty good chunk of the respondents say they use chemicals largely to conform to equipment manufacturers' specifications. So, in your experience, do you know what chemical that might be, what kind of chemical, and what type? Looking at all these specs, what would be an example of a specification that it would allow you to conform to?
Well, if I look at those specifications, really it's not about chemical addition, it's about demineralizing the water. Because if you look at the wide range of chemicals, particularly either, I'll use the one in the upper left-hand corner, it's going to be very difficult to chemically treat to take care of all of those concerns, whereas if I do it as a demineralizing the water, I've wiped all of that clean from the fill water.
There are some boilers that ship with a chemical, though. I don't know if you remember when the MZ boilers first came out. They were one of the first aluminum boilers that you guys probably saw out there, and they would ship a pint of that Inabol inhibitor that puts in there. And I know most of the aluminum boiler manufacturers now will give you a choice of 3 brands that they suggest you put in. Typically, Romar, Fernox, and Sentinel are brands that they give you an actual product name that they recommend that you use on those aluminum boilers. So they're the ones that seem to be most sensitive about having a fix in there in addition to the water that you're putting in there. So I think that's where we came up with why you're getting this response on the bottom. Probably the aluminum boiler guys are saying, well, wait a second, the manual says to use one of these 3 products in there. So, that's why.
Typically looking at either fixing the pH or a film former to help protect the aluminum.
Yeah. Yeah.
Yeah, but there was a couple of comments that came in the same way. Some of the boiler manufacturers list.
Yeah.
Okay, so that's where people are coming from.
Yeah,
okay.
Feedback on that.
Yeah, and I think the caveat there is to make sure the water quality is good enough that the inhibitor will actually work properly. Because, as the chemical guys have actually said themselves, if you get higher than typically 25 parts per million of sulfates and chlorides, it will prevent the inhibitors from working correctly.
Well, let's do this. We've got 5 minutes left, and the next slide jumps into glycols. Maybe that's a good place to start next month because it is kind of another topic, and I know there's a lot of glycol users out there. So I know Mike's got a stack of questions. Let's use the last couple minutes here and see if there's good input or questions. If you prefer to type it in, we've got plenty of those.
There's some glycol questions.
Oh, glycol questions.
Hold on those.
Yeah, I think you saw my next slide there.
Well, maybe, Bob, you can show the next few slides, and then guys that can see what we're looking to present next April is only what?
30 days.
30 days. Yeah.
Yeah, so that's where we're going to go with you next on glycol is because we know a lot of you guys, especially with the out in the west and the snowmelt people, it's a must. There's no option not to have glycol in some of these systems. So knowing that, how do I make sure that I got it right, that I've got the inhibitors, that I mixed it right, that I clean my system. So here's where we'll start with that poll question. I don't know how far you want to go into this, but
I just wanted to give guys an idea of what our slides look like and go into.
Yeah.
And then what we'd like to do is whatever questions you still have, and if you guys like this format where guys can ask questions, all right, we had 3 or 4 today that were able to talk live. Let us know that, because if so, we'll continue this. We'll do it again in April, and then we'll address glycol, which is a very, as we know, and especially up in Canada and also northern United States, is pretty popular for systems. We'll get into measurement devices, and we didn't get into devices that manufacturers have for addressing the problems that can occur from corrosion, such as sedimentation. Yeah. We didn't get into dirt separators, wide strainers, and we really didn't get into air separators in any large degree. So those are all things that we can tee up for the next one.
And I think one of our best attended webinars that we've ever done was when we had the glycol. We had a fellow from Dow, heat transfer division, that did a glycol. I think we had like 300 people showed up there. So we know that's on your mind, and maybe we need to go into that a little bit more. Maybe we'll get a glycol expert or two on board, that if there's something specific to the chemical, that we can have them on with us next month to help out with that. So any other questions that we can do here for
No, I think that's about it. It's just
all right, well, the housekeeping, then let me get down to, so this is what we didn't get to, so let me get down to the last couple of housekeeping. I guess we got a little bit. These are some of the, just if you guys want to go there, I went and found all these, which you'll see on your slides that we'll send you, as far as you want to look into these standards that are out there and learn a little bit more about what they're doing in these other countries, which, by the way, in some of these countries like Germany, that's part of the inspection now. They're going to put a combustion analyzer on that boiler you put in. They're going to inspect for, piping, the way you put it in there, and then they're going to look at your fluid or your water in there. So those are probably the 3 most common.
Bob, the VDI standard, the 2035 of Germany. And by the way, Germany has a boiler market, a hydronics market that's 2 or 3 times the size of all of North America. So there's a lot of, obviously, thinking behind these water quality standards that we in the United States don't yet have in place, whether U.S. or Canada. But there are 2 parts to it, as Bob mentioned. I encourage you to go on their website, as we show here, because you can download the PDF.
Yeah.
And what would you say? Probably about a half an hour read between the 2
pages or something like that. So.
And okay, maybe more than a half an hour. But it's very good technical information.
There it is.
And here we go.
And I see some of the things that we've been talking about there on the right, or what they go into every one of these and talk about. Okay, this is what you need to know, and this is what you need to do. And you can see over, I don't know how much, well, you can see that. It's getting pretty small print there. But you see they talk about copper and aluminum and stainless and all that. So they've done their homework on this topic, and maybe someday the U.S. will adopt this or a version of this, because this is really pretty comprehensive. So it's just like, we don't want to overwhelm you here either and with information. So read that as you have time, and then let me get down to see, we had a lot of slides. I don't think, so we don't have any housekeeping at the end, because we don't have the excellence going or anything else. So with that, I guess we'll say thanks, everybody. Thanks for playing the game and participating with us, and we'll get to the typed in questions, and it sounds like we're going to go with this next month. So
April.
April, sorry, because Jody and Kevin are next month. So April, bring your questions again, or additional questions you have, and thank you, everybody. Thanks for supporting Caleffi.